Now that we spent a good deal of time talking about the electric field and electric forces and how they can push charges either across surfaces or through circuits and things like that, it's now time to begin a new unit, specifically Unit 5, Electromagnetism, and start seeing how electric fields can actually lead us to a different type of field, magnetic fields. Now, we spent a good deal of time in AP Physics 1 talking about gravitational fields and forces, and we began a conversation there, and in this course talking about electric fields and forces. But we've not talked about magnetic fields really at all, which is kind of surprising because you experience these a lot of times in your everyday life. But we've not really talked about, okay, what are they? What is causing them? How do they behave? So that's what today's focus is going to be, is specifically on magnetism. So let's say I have a bar magnet here, and this bar magnet, I'm going to go ahead and say one side is marked with an X, and what we're going to do is we're going to place a compass at various points around this bar magnet, and if we do that, we start seeing that this compass is attracted to the side, the compass needle, is attracted to the side without the X, and seems to be pushed away from the side with the X. And this continues as I begin to move the compass to various positions. The needle is continually pulled towards the unmarked side and pushed away from the marked side. So let's say we continued our investigation and we got something that was magnetic, like for instance, iron filings. So iron filings are kind of like iron dust. It's these little iron shavings. And let's say we sprinkled these around this bar magnet, we would start to get something that looks like this. We would start to get these lines where the filings are lining up with each other from one end of the magnet to the other, and this starts to look familiar because it starts to look a lot like an electric dipole. In other words, a positive and a negative charge. When we drew the electric field lines, we see that the shape is very, very similar to the shape that these iron filings are taking on. And let's go and bring in a second bar magnet, and let's put it so that one marked end is next to one unmarked end, and if we sprinkle the iron filings again, well, we would see that these shape of lines we're getting from one end of the magnet to the other really go from the marked to the unmarked end between them as well, and once again, this very clearly resembles what we see when we put positive and negative charges by each other. But okay, let's go ahead and flip one of these magnets around and actually have the two positive ends towards each other. And when we sprinkle iron filings, we start seeing these start to what look like oppose each other, just like if we put positive and positive charges next to each other. Or, for instance, negatives and negatives. So what these trials are beginning to show us is that every magnet is in essence a dipole, meaning it has two poles specifically that we label as the North Pole and the South Pole. Now specifically, okay, let's go back to the compass situation. The compass points towards the south pole of a magnet and points away from the north pole of a magnet. And if we start to bring, let's say, for instance, a north pole and a south pole together, well, then these would be unlike poles and they begin to attract each other. And you've experienced this. If you have two magnets, they're either going to repel or they're going to attract, depending on how exactly you arrange them. And if we get the unlike poles towards each other, they will attract. And if we get the like poles towards each other, they will, in fact, repel. Exactly like electric charges. Instead of having positive and negative charges, now we have north poles and south poles. Well, how are these magnets attracting and repelling each other? How are they applying forces to each other without coming into contact? Well, much like gravitational forces and electric forces, magnetic forces are based in essence, magnetic fields. These magnetic fields are three-dimensional alterations of space created by a magnet that cause other magnets nearby to either feel attracted or repelled due to their presence in this field. Now, a couple things here. First off, we typically abbreviate magnetic fields with a capital B. Not 100% sure why we do that. I believe it just comes down to the notation it was originally written down in by some of the first physicists who studied it. Additionally, when we measure the intensity of a magnetic field, that intensity we label in units of Teslas, which we abbreviate with a capital T. And a Tesla is a really, really big magnetic field. Typically speaking, we deal in fractions of a Tesla. The Earth's magnetic field is a fraction of a Tesla. Now, these magnetic fields we can represent in a couple different ways. So if I have a north pole and a south pole here, we can either draw between the magnetic field vectors. We're keeping in mind the bigger vectors means that we have a bigger field, and if they are smaller vectors, we have a smaller field, and we could also have magnetic field lines. And remember, how do we figure out the strength of these lines? Well, we just look at the density. For instance, the lines are closer together here, the magnetic field is stronger. They're further spaced apart out here, the magnetic field is weaker. But one more thing we need to note is that magnetic fields are ultimately vector fields, so they not only have magnitude, they have direction. And how do we define the direction is specifically as going from a north pole to a south pole. All magnetic fields are defined as going from north to south, just like electric fields are defined as going from positive to negative. And this is specifically the direction that a compass will point. So if I bring a compass in between these magnets, it will point in the direction of the specifically labeled and defined magnetic field. Okay, well, let's say we take one of these bar magnets, so if it's north pole and the south pole, and I take it and I smash it against something and I break it in half. Well, now I've separated the poles, right? Because they're no longer connected to each other. But you would actually find out that in doing this, we've created is actually two new magnets. Now on this magnet, we would have a north pole and a south pole. This one we have a north pole and a south pole. So breaking it in half does not make them no longer dipoles. We just create a new dipole. So if I break them in half again, well, once again, we're separating the two halves. I've now created four magnets. So every magnet must have two poles. There is no such thing, as far as we know, as a magnetic monopole, meaning I cannot have a north or south pole by itself. This is unlike electric charges. Electric charges, you can have positive and negative charges alone. That is not the case for magnetic poles. But what happens if we kept breaking down those magnets into smaller and smaller and smaller and smaller pieces? Well, eventually we would get to individual atoms. And this actually tells us that individual atoms of magnets actually behave like magnetic dipoles themselves. These atoms have what is known as a magnetic moment. And this magnetic moment, its size, the number that quantifies it, will tell you how magnetic this atom is, and its direction points in the direction of its magnetic field. So this is one particular atom with its magnetic moment. Now, the thing is, though, is that what happens if we broke this atom down into even smaller parts? We would actually see that even subatomic particles behave like magnetic dipoles and even have their own magnetic moments or their own north and south poles, respectively. So looking here, I have, for instance, two electrons, and we have one, this mu m here, that really is just a symbol for magnetic moment. So this tells me the magnetic moment of this one is pointed upward, the magnetic moment of this one is pointed downward. And this is closely related to a quantum mechanical property of electrons known as spin. We would say that an electron with a magnetic moment pointing upward would be quote-unquote spin up. And an electron with its magnetic moment pointing downward would be quote-unquote spin down. And they pair based on this spin up and spin down property. Now, real quick note, they are not actually physically spinning. That is not what is happening here. Spin is just a property that we label that when electrons are used in certain experiments, they seem to have some sort of inherent spin nature, but it's just really a term. It is not a physical spin. Now, based on what I just said, it's not surprising that magnetism can be a bit complicated because ultimately it comes down to the quantum mechanics of subatomic particles. And there's actually many, many different forms of magnetism. We have diamagnetism, paramagnetism, ferromagnetism, antiferromagnetism, and even ferromagnetism. And we could spend an entire semester talking about all of these, but really the one we're going to focus on the most is ferromagnetism. That's because ferromagnetism is the type that you're most intimately familiar with, because any magnet that you've experienced, like a magnet on your fridge or anything like that, a quote-unquote permanent magnet, is an example of ferromagnetism. So what exactly is ferromagnetism? Well, ferromagnetism is a behavior displayed by materials that we label as ferromagnetic that can become, in essence, permanent magnets. We can move them around away from other magnetic fields and they still keep their magnetic properties. They are, one, strongly attracted to magnetic fields, so if in placed in the field they're going to be attracted to it, and they can also reinforce already existing magnetic fields. So if you have a magnetic field, if I bring a ferromagnetic to it, I can make it even stronger. And how are these materials different from other materials? Well, it's a result of, one, these materials having unpaired electrons. In essence, when their orbital shells are filling out, we've got electrons in the shell that are either magnetic moment spin up or spin down, and they don't have their counterpart. And when we get multiple of these, you're going to, in essence, have all of that effect accumulating, so we get a larger magnetic effect in one direction. And it's also, in essence, a part of their crystal structure, that when certain elements crystallize in these patterns of atoms, they do it in such a way that their magnetic moments of their atoms are going to line up. And the three most common ferromagnetic materials are iron, cobalt, and nickel, and alloys of these. Now, there are some other more rare examples, particularly like in the bottom of the periodic table, but these are the three that you're going to experience the most when we talk about ferromagnetic things. Something else that's unique about ferromagnetic materials specifically is that their atoms will clump together into these basically little pieces of material that have all of the magnetic moments of the atoms aligned. And these are called magnetic domains. These are pieces inside the material where all of the atoms nearby, they're all lined up with their magnetic moments in the same direction. And these emerge spontaneously. It really has to do with them just being a lower energy state. Now, these magnetic domains, so if I zoom in on like this block of iron here, these magnetic domains, each domain has all of the atoms pointed in a certain direction, but if you look at all the domains, they are randomly arranged. And there's no net magnetism from this piece of iron, because this piece of iron in this domain has its magnetic field pointed this way, this one has its magnetic field pointed that way, etc. So how can I magnetize this block of iron and make it into a permanent magnet? Well, first I immerse it in a external magnetic field. I put it in the magnetic field I've generated somewhere else, and that is going to, in essence, cause all of the atoms in these magnetic domains to start to shift. And they're going to start aligning up with this magnetic field, and that's going to cause some of the magnetic domains to shift in position. It's going to cause some of them to literally merge together until all of the atoms in this piece of iron are all lined up with the magnetic field. And eventually, we'll reach a state where all the atoms are pointed that way, and if we remove the field, they stay aligned in this position. And we've now created a piece of iron with a magnetic field pointed in this direction. So these domains have grown and shifted. And now we have a permanent magnet. I can take this magnet other places and it's going to be generating its own magnetic field. So how do we make this no longer a permanent magnet? How do we demagnetize it? Well, we want the magnetic domains to no longer be aligned, to break apart and be pointed in different directions. And that really can be caused by simply adding vibrations to the system, because when we vibrate them, the atoms will start to shift around a bit, and eventually they're just going to get knocked out of position. Now, one way we can do this is we can literally just take it and smack it really hard against something, and that will cause all the magnetic moments to vibrate enough to start shifting around. But we could also just heat it up. If we heat up this block of iron, all of the atoms will vibrate, they will get out of their arrangement, and now all of a sudden the magnetic domains are no longer aligned with each other. Now, this is at high temperature, so this doesn't just happen at room temperature. You need to heat it up quite a bit, but for certain materials that temperature will be less. So what key takeaways do we have for this first lesson in the unit of electromagnetism, specifically talking about the magnetism portion? Well, one, can we describe how magnetic poles interact? That unlike poles attract each other, so north and south poles, and like poles repel, north and south and south, and that each magnet has two poles. Can we draw magnetic field vectors and lines for different arrangements of magnets, keeping in mind that the vectors and the lines point from north poles to south poles? Can we describe how ferromagnetic materials behave, essentially what makes them quote-unquote ferromagnetic and therefore different from other materials? And can we explain what magnetic domains are and how they change when we take a ferromagnetic material or a permanently magnetic material and either magnetize it or demagnetize it?